Okay, so just for those of you who aren't too familiar with boundary nonlinear analysis, I'll just go over sort of a quick sort of overview of the basic concepts of it, and then we'll just jump right into the presentation with MIDAS Civil. Okay, so just a couple of key points about boundary nonlinear analysis with MIDAS Civil, also known as geometric linear. So the first two sort of analysis types that are available in MIDAS Civil are nonlinear modal analysis and nonlinear direct integration. So what we're doing is we'll be focusing on nonlinear modal analysis. Nonlinear direct integration is something that we can go over sort of at a later time. As far as the sort of elements that we'll be using, the first kind that I want to talk about are element types of the nonlinear link. So these are spring/linear dashpots or spring linear dashpots. And then we also have force type nonlinear links, so viscoelastic dampers, gaps, also known as hooks, hysteric systems, lead rubber bearings, also known as LRBs. We'll be focusing on this one in particular today, how to model those and how to define those. And then we'll be also be going over the friction pendulum system, FPV. So we actually won't be going into a live demonstration of how to use this, but I will show you where the input is available to you. Okay, so let's talk about some seismic design procedures. So for conventional seismic design, when earthquake energy or seismic energy is applied to the system, the structure experiences plastic deformation and has a very high repair cost. This leads to damage in contents. And for those of you who work in sort of higher seismic regions, you'll know that sort of conventional seismic design standards aren't really up to par for the type of projects that you're doing. For those of you who are in low seismic zones, usually conventional seismic design won't be able to suffice. But for those of you who, once again, work in higher seismic areas where, earthquakes really need to be taken into account, you're probably using something more along the lines of what's listed here on the right side of the slide. So for base isolation, also known as passive vibration control, here we have the earthquake energy, but as you can see, most of it is being dissipated into the isolator or the damper. So this leads to, inelastic behavior, easy replacements. So for example, if you have, an isolator or damper that's damaged during an earthquake, it can be easily or, very simply replaced. So what's really great about these isolators and dampers is mainly that it absorbs most of the earthquake energy. So it keeps most of it away from your structure, which is what you want to sort of be stable. So as you can see, what happens when the structure receives the energy that's sort of left over from the dampers and isolators is there's nearly sort of elastic behavior, there's a very low or unnecessary repairs, and then also the protection of your structure is maintained. So, this learning how to model these isolators and dampers and how to, sort of create a simulation with them is very key, especially for bridge models. So let's talk more about base isolation. So let's talk about some just basic sort of fundamentals. And then we'll talk about the lead rubber bearings and then friction pendulum system. So these are the three main sort of topics when it comes to base isolation. And as I said, both of these can be modeled in MIDAS Civil. So the main sort of concept of the base isolation is as follows. If you look to the picture here in the top left, as you can see, what we have is sort of like this concrete slab here, a steel plate that's being loaded on top of sort of a set of bearings here corresponding to the block. And then we have a glass of water here. And as you can see, when seismic load or any sort of vibration is applied to the system, the water, it splashes around, but ultimately the cup stays for the most part stable just because the energy is dissipated in these bearings here. Now if you look to the bottom here, as you can see how this principle is applied to buildings. So what we have here is here's your main sort of superstructure, here's your foundation, but then between the foundation and your superstructure you have these isolators. And what happens is when there's movement in the ground, when there's seismic loading, these isolators will absorb the energy and sort of dissipate it so that it doesn't cause any harm or to the integrity of the structure. And as you can see if you look to the right here, here's an example on the top right here. There's a fixed base. So in other words, there's no sort of isolators applied to the foundation of the building. So when seismic loading does occur, most of the loading or most of the energy goes directly to the structure itself, which can cause high amounts of damage and ultimately failure. However, if you have these base isolators here, as you can see, the building moves, but because these isolators absorb the energy. So ultimately, even though the building is allowed to move, it moves with the earthquake, which ultimately saves it from having any sort of large-scale structural damage. So that's pretty much the main principle that's being applied. So during today's demonstration, what we'll be showing is how to model specifically these isolators, how to define the properties for them, and also how to interpret results that are given from them. Okay, so here we have a couple of sort of graphs here that illustrate the fundamentals, more of a base isolation. So as you can see, with pseudo-acceleration or the response spectrum method, you'll have a period shift here due to the damping. So as you can see, as a period increases, you can see a sort of a major shift here in the damping. So ultimately, the main sort of points to remember is that isolator flexibility after yielding, there's force reduction, building damage reduction, and isolator displacement increases. So ultimately, the main sort of purpose of these isolators is to reduce damage or to reduce the energy that is sort of directed towards the building during seismic loading or dynamic loading. And here we have an increase in damping. So as you can see here, we have energy dissipation. We have isolator displacement reduction, also building damage reduction. So these are just a couple of graphs that sort of illustrate what happens when you have sort of seismic loading applied to a building and when there's isolators involved. So the main point to get across is that these isolators, absorb the energy. Okay, and here's sort of like a cross-section of lead rubber bearings. So for those of you who've worked with these structures before, you'll know that this is sort of what they look like. This is what it looks like sort of coming out of the factory. So it's just sort of like this large sort of cylindrical rubber bearing or rubber plate. And what you do is you mount it to the top of your structure. So typically this bottom portion here would maybe be sort of linked to the abutment of your bridge, or possibly, it'll be linked to your pier cap. And then this rubber bearing or this plate here will link to your superstructure. So these are just sort of the main parts here. So as you can see, there's a rubber cover, you get your mounting plate, steel reinforced plates in the center. Also internal rubber layers provide lateral flexibility. And then you also have this energy dissipation core, which allows it to, in a sort of a very limited sense, to sort of swivel. So as you can see here, the main sort of things to remember is that it dissipates energy, it's very good for wind resistance, and it has deformation recovery, which is good. So, even after being sort of subjected to large amounts of loading, it can still return to its original shape, which is very key. Okay, and then the other system that we have, sort of an alternative, is something known as the friction pendulum system. So as you can see here, it sort of follows this basic concept, just the idea of sort of a pendulum type motion. So if you look to the bottom left here, when, for example, when the structure is subjected to seismic loading, you'll have a sort of a pendulum type motion happening here. So as you can see, the energy will be dissipated in this area here. So there'll be a certain amount of movement for your superstructure, which is to be expected, but this sort of movement from the friction pendulum system allows the superstructure to be sort of safe, and it'll have less energy directed to it. So most of the energy will be dissipated in these areas here. Okay, so that's just the basic, just sort of gist of these isolators. So if you have any more questions about them, feel free to just email me at the end of the session, and I can provide you with more information. So what I'll be doing now is I'll just be going over a brief demonstration of how to model these types of projects in MIDAS Civil. So just give me a second here and let me sort of organize my files. Okay, here we go. So keep in mind that for this demonstration, I'm actually referring to a tutorial that we have posted on our website specifically for nonlinear time history analysis of bridges using these seismic isolators. And what I'll do is I'll scroll down to the tutorial here, and I'll just give a sort of an overview of what we'll be going over. So as you can see, this example focuses on a procedure for performing nonlinear boundary time history analysis. So ultimately, the modeling process will be omitted. So I won't be going over the modeling of the bridge itself. Moreover, or actually more precisely, I'll be focusing on just defining the links, creating them, defining the load cases, and then going over the results. So the main sort of points of the procedure, or the parts that I'll be going over today, will be as follows. So I'll be defining the properties of the nonlinear links, and I'll be inputting the nonlinear links into the model. Then I'll enter the analysis conditions for time history analysis. Then I'll perform the analysis itself, and then I'll go over how to extract a couple of the results. So as you can see, you know, all of my steps will be recorded. So in addition to having a recording of the session, you'll also have access to this tutorial. And as you can see, everything that I'll be going over will be sort of listed out here very clearly. So now, here's the sort of a blank sort of project file for MIDAS Civil. Let me just make sure I have my units correct, meters and tons, okay? So another great sort of function of MIDAS Civil is that if you have like a completed model file, and let's say you want to maybe you have an alternate version of a sort of model, or if you have different sort of loads or whatever that you want to create for it, instead of having to recreate the entire model or create like a duplicate from an existing one, you actually just import the model file or the model directly. You can do that just by going to the top left here to the MIDAS Civil icon, select Import, and then select this top option here, MIDAS Civil MCT file. So this allows you to import a model from another file just directly into this new project that you're working on. So what I'll do is I'll select this, and as you can see, I already have my spot or my sort of location selected. What you can do is you can sort of sort through the files of your computer. If you find another MIDAS Civil file, all you have to do is double click on it, and your file will be imported directly. So what I'll do is I'll double click. And as you can see, I have my bridge imported. So this is a steel box girder type bridge. And let me just sort of give you a better view here. As you can see, it's 3 spans. Here are my piers and my pier caps. And then I believe the abutments will just be here on the edges. So what I'll be doing is I'll be assigning my lead rubber bearings to these areas here. And let me go to the wireframe here. So sometimes if you just want to see the beam diagrams instead of the full sections, what you can do is you can click on this option here, hidden, and as you can see now I have my beam diagrams. So let's take a closer look here at what's going on with my model. So if you zoom in, and another great option that you can use to zoom in is if you go to the right here, you have this set of icons that allows you to change your display modes. Just go here and then just use this magnifying glass, the zoom option. We're going to zoom in on our model. So as you can see, currently it looks like there's no sort of nodal connectivity between these nodes here, but actually I do have my rigid links for these sections here, but I just don't have them displayed. So if you want to display any sort of rigid links that you have created before, just go here to this option under Display, and it has like sort of lists of all the different sort of elements that you can choose to hide or display. So rigid links count as boundaries, so what we'll do is we'll go to the Boundary tab, and then just select Rigid Link, and click OK. So as you can see, if you look closely now, we have sort of a series, or we have a couple of rigid links that ensure nodal connectivity between these nodes over here. Okay, but something that we don't have is nodal connectivity established from, let me turn on the node numbers too. For example, from node 94 to 96, there's no connectivity, and from 93 to 95, there's no connectivity. So these portions are where the bridge's abutment meets sort of the edges or the foundation of the opposing sides of the ground. So what I'll do is I can go here too. Let me turn the node numbers off. As you can see, I have my rigid links applied here from the pier cap to the pier. But then if I go over here, as you can see, I don't have any nodal connectivity. I have my rigid links, but if I zoom in sort of further here, you'll see that there's sort of an empty space here where my LRB or my lead rubber bearings are going to be. And the same sort of applies to the other side of the bridge here. So there's no nodal connectivity over here or over here. So what I need to do before I sort of assign my lead rubber bearings is first I need to define the properties for them. In order to do that, I'll have to, and actually let me just show you the spreadsheet real quick, what I have here. So going back to the tutorial, as you can see, it's good to have all of your material properties sort of ready for you before you go to your modeling. So if you're sort of creating, lead rubber bearings, just make sure that you have these sort of properties defined already. So everything from effective stiffness, effective damping, yield strength, etc. Make sure to have them for each of your lead rubber bearings. And for this project, we'll have a set of lead rubber bearings for the abutment, and we'll also have another set for the piers. And as you can see, they have sort of different properties. So these are just a couple of things that you need to take into account before you get to your modeling. So once you have your properties defined, you'll need to input them into the program. So in order to do that, just go to the boundary option, and then if you go over here to the general link option, just click on that, and then select general link properties, ... Okay, so right now this blank sort of empty table comes up. The reason it's empty is because I don't have any properties defined as of yet. So what I'll do is I'll go to add, and then I'll have this input menu. And here, it's fairly simple. You just have to give your LRB a name. So for the LRBs of the abutment, let's just name this LRB dash A for LRB abutment. And then make sure this is force. And then here under property type, just go to the drop-down menu. And as you can see, we have your FPS, your friction pendulum isolator, and then you also have your lead rubber bearing isolator. So let's select this one for lead rubber bearing. And then you just need to define your linear properties. So check on dx, dy, and dz, and then just type in your values. And also just double checking again that I'm in the right units here, so tons and meters, good. And then just type in your values. So this will be 47,100. This will be 336.1. This will be 336.1 as well. And then I'll also turn on dy and dz. So for these properties, this one will be 1099. This will be 1569. And then for my post yield stiffness, 0.00897. Now these values, typically you don't really have to calculate them yourself. If you just sort of order these, they'll come with these sort of properties sort of assigned to them, or sort of outlined into them. So just go here, and then this will be the same values in the y direction. Just enter these in. Okay, they're all there. Okay, very good. And then we'll click apply. So, a question that's brought up a lot is what's the difference between OK and apply in the drop-down menu, or excuse me, in the input menu. The main difference is, well, let's talk about how they're the same first. The thing that makes them the same is that if you click either OK or apply, the new property will be created. The difference is if you click OK, your new property will be created, and then this input menu will disappear. Whereas if you click apply, the new property will be created, but this input menu will stay here. So the apply option is useful when you're creating, let's say, for example, multiple properties at once. Instead of having to click OK and then sort of open up the input menu again, you can just click apply and then just go straight into creating your new property. So as you can see, if I click apply, my new property is created, but this input menu is still open. So let's say I had like 5 of these I had to create. It'd be really cumbersome to have this input menu close each time and have to reopen it. So that's what that option is for. So now for my second lead rubber bearing, put LRB-B, and then I just have to enter my values. Actually, LRB-P, P for pier. Okay, so make sure you have the right property type selected. And then, let me save this real quick. And then what I do is I just enter in my values. So this one will be 1289000. This one will be 702.2, and this will be 702.2 as well. Then I have dy and dz checked on, good. And then I'll open this up, and I just enter in the values for this one. So this is 2204. This is 33.63, and then the post yield stiffness is 0.0862. Okay, very good. So now I have the my properties for my LRBs defined. So I'll click OK this time, As you can see, the input menu disappears and my second property has been defined. So it's very simple, just to create your link properties. So once again, just the path is go to General Link. So make sure to click on the drop-down menu. So General Link Properties, then just click Add, and then this input menu will allow you to put all the properties that you need for your isolators. Okay. So now if I go to my work window, go to Works here. As you can see here, I have my two properties, but they're in blue, which means they haven't been in use in the model yet. So what I'll do next is I'll actually create the links. So let's go back to the zoom option here, and we'll go to the bottom left. And then in order to create your links, just go to General Link. As you can see, this input menu will come up, and it allows you to select from the sort of properties that you've created. So for the links here in the abutment, make sure it's LRBA, and then from this point, you just have to connect the two nodes. So what we'll do is we'll go make sure that you check into this box here. You want to make sure actually that this box turns green and that this piece here is flashing. So when it's green and that's flashing, that means the program is ready for you to input the coordinates or to select your nodes. So just put your cursor over the nodes here. As you can see, LRBA has been assigned here and here. Okay, so now we have no connectivity. All right, and then if I click Close, as you can see, LRBA is in black now, which means that it's in use at least once in the model. All right, so from this point, all we have to do is assign our different isolators to our peers and to the other abutment. So I'll do that real quick. And once again, you can just use the zoom option here, and you can just box in what you need to see. All right, so now for this one, make sure we're still in boundary, go to General Link. Now change the property from LRBA to LRBP for the peer, and then click in this box here, two nodes. So as you can see, if I don't click in this box, if I go here, nothing happens. That means the program doesn't recognize it trying to put in your link yet. So before you put in your link, make sure you click in this box. Now the program is ready to input it for you. So here's one, and over here is two. Okay. If I look over here, as you can see, now they're both in use because they're both in black. Okay, now I just need to do the same thing really quick for my second peer and my second abutment. Go here. Okay, go to General Link. Make sure this is LRBP. Okay, and then we'll connect these nodes. There we go. And LRBA. There we go. Now our isolators have been input. Okay, so now that we have our isolators in place, our next step is to define our functions or our seismic loading, which it sort of takes a few more steps because you have to define your loading, define your load cases, etc. And there's also a couple of adjustments that you actually need to make as far as sort of how your mass is sort of taken into account. So what I'll do now is I'll go into the next step, which will be to sort of go over all of your sort of mass inputs. So some important things to remember is that there are three types of masses that can be defined: structure mass, nodal mass, and load to mass. So detailed applications of each type of mass are explained in the online manual. So if you have any sort of more specific questions about that, feel free to contact us or feel free to go to the manual. They have a lot of answers can be found there. But the main thing to remember now is that for nonlinear modal time history analysis with general links, the mass should be assigned to all the nodes to which general links are connected. So in this example, the structure mass and the load mass are used. So before I go into sort of going into that, how to sort of alter the masses, let me just sort of show you the load we have here. So as you can see here, under static load, I have the self weight, so the structure itself, and I also have a couple of beam loads. So I think this is probably like the dead walk for a sidewalk or something. I can't remember exactly what it is for this project. Just keep in mind that there is a distributed load going along the sides here. Now for seismic analysis, in order for these loads to be taken into account, you have to model them as masses. So for seismic analysis, there are three main things that are taken into account. There's stiffness, damping, and mass. So stiffness and damping, I've already sort of defined, but mass still needs to be defined, particularly for these loads. So let me just undisplay these now. In order to undisplay it, just select it and then just right-click, and then these options let you sort of display it or undisplay it as you see fit. So first, to change my or to convert the self-weight of the elements into sort of into a mass, go all the way over here to structure, and then go to structure type. Okay. So as you can see, here we have the different options we have for our structure type. So let's leave it as 3D, but now the thing we need to change is we need to convert the self-weight into masses. So currently the box is checked off, just make sure this is checked on now. Okay, perfect. And then, let's just leave it to convert to X, Y, and Z because we want it in 3 dimensions. So that's really all you have to do to model the self-weight as a mass, is just go to this option here and then check this on. So click OK, and we're good. Okay, so now our next step would be to model our loads as masses, or in other words, to convert our beam loads to masses. So in order to do that, just go to Load, and then go to Loads to Masses. So it's right under here under this tab, under Structure Loads / Masses, and then this option here, Loads to Masses, will allow you to do that. So go here, and then just select the mass direction, X, Y, and Z, because we want it in 3 dimensions. So nodal load, beam load, and pressure load, okay. And then another thing we need to do is we have our dead load selected, scale factor is 1, that's good. Now we just need to add it. Okay, so we have our dead load here, and then just click OK. And as you can see, when that happens, you can see these sort of boxes start to show up, which indicate to you that these beam loads, that distributed load that you had, will now be modeled as part of the mass. So that way, when the seismic loading or the seismic analysis is being done, all of this will be taken into account, which will give you a much more sort of realistic sort of set of results. Okay, so once you have those, once you have your structure masses and your load or once you have your structure loads and your beam loads modeled as masses, the next thing you need to do is to define your time history data. Okay, so as far as time history functions are concerned, there's a couple of important things to remember. Go here. So there's a couple of important things to remember. First off, unlike linear analysis, the principle of superposition does not apply to nonlinear analysis. This is very key. So this example pertains to analysis for both dead load and seismic load, but it is not correct to linearly combine the separate results due to each load afterwards. So for time history analysis, we need to consider both loads. That's dead load and seismic load we're talking about. We need to consider both loads acting simultaneously. So in order to reflect dead load in time history analysis, we have to create something called a time-varying static load function. So this function, it just basically creates a condition in which the dead load is in place at the time of performing the time history analysis for the seismic load. So we'll call this a ramp function. Okay, so a ramp function is assigned to the static dead load, and what we'll do is we'll use a couple of time history graphs, or just sort of preset graphs for our project. Okay, so in order to go to our time history load, make sure you're under the Load tab, then go to over here under the Load type, select Seismic, and then select Time History Data, which is right over, I think it's over here. Okay, so Time History Data function. And then what we'll do, we don't have, as you can see, we don't have any functions created yet, but we'll go to Add Time Function, this option here. And what we'll do is we'll create a ramp function. So we'll name it ramp. Okay, and then we'll enter in. Okay, make sure this is normal first off, and then scale factor is 1. Good. And then we'll just enter in our function here. So we'll start off with 0 seconds. It'll be 0, and then 2.5 seconds, and it'll be 1. And then 5 seconds, and it'll be 1. Okay, so that'll be our first function. So we'll click OK, or actually we'll click Apply. So keep this input menu up. So as you can see, the new function is created, and then this is cleared to allow us to create another function. So what we'll do now is we'll select sort of 2 functions that are sort of preset, or that are just sort of available just in the database, just to keep things simple. I mean, if you do have your own sort of time history function, as long as you have it as in Excel format, you can just copy it and paste it into here. But if you are just okay with using something in the database, you can just refer to this database, which I'll show you in just a second. So first, let's name this function. Let's name this, because I'm going to be using an earthquake called El Centro. So we'll name this L Centro and then H for the first one, and go to earthquake. So as you can see, if you go to this drop-down menu, you have a very sort of extensive list of different earthquakes that you can use in different parts of the world. So we'll just use the El Centro site, 270 degrees. That will be our first one. Click OK, and then also important to know just the peak and the duration. These are things that can be important to you. So click OK. So that'll be our first function. Then we'll click Apply. As you can see, it's listed there now. So now we'll create a second function. El Centro T, so let's name it cent underscore T. Okay, and then we'll go to earthquake, and then we'll select the second one, El Centro site 180 degrees. Okay, here's your function. Then just click OK. And now, as you can see, we have our ramp, for sort of like the dead load, and then we have the two sort of functions for our seismic loading, or our time history loading. Okay, so now that we have that done, the next thing we need to do is we need to define our eigenvalue analysis. Now, something that I had alluded to previously was that there are two sort of major methods for performing time history analysis. So those methods are the modal superposition method and the direct integration method. Let me open up the option here real quick. So if you go to load and then load cases, as you can see, before you add any of your load cases, you'll need to define your eigenvalue analysis control. So let's open up this tab here. And then, something important to remember though, excuse me, is that the eigenvalue analysis control data need to be specified before defining your time history cases. So for eigenvalue analysis, MIDAS Civil, as you can see, provides eigenvectors, the method, and the eigenvectors method, or the Ritz vectors method. So the Ritz vectors method is strongly recommended when nonlinear modal time history analysis is performed with general links. However, in this case, the general link force vectors must be included in the starting load vectors in order to include deformations of general links to calculate the starting load vectors. So in this example, what we'll do is we'll use the Ritz vectors method with checking on the include GL link force vectors. We'll check this on. So keep in mind that once again, when nonlinear modal time history analysis is performed with general links, you want to use the Ritz vectors method. Okay. So now that we have this checked on, the next thing we need to do is just define sort of our controls here. So for the dead load case, we just want to select, for example, the number of generations, which will be 1, and then we'll just click Add or OK. And then also we have to define our ground accelerations, both in the X and the Y direction. So in the X direction, and we'll make it 8. And then make sure the vector here is 1. Then we'll add it. And ground acceleration of Y this needs to be 8 as well. We'll add it. Okay, and that's just how you set up your eigenvalue analysis control. So once again, when you're using these general links with seismic analysis, make sure you go into this option here and you just change it to Ritz vectors, and you just enter in your vectors accordingly. Just click OK. Now that's taken into account here. Okay, so now that that's done, we can finally define our time history load cases. So in order to do so, just go here to Add. Okay, so first let's name our dead load. And then we're going to select nonlinear for our analysis type. So we're going to use the analysis method will be modal, and the time history type is transient. So the end time here will be 5 seconds. Okay. So the finish time until which the time history analysis is required. So the duration of seismic data should always be considered to find your end time. Okay. So for the time increment here, let's name it as 0.002. So the time increment of a time history analysis, it significantly affects the accuracy of the results. So just a common rule of thumb for determining the time increment is to use at least 1/10 of the smaller period of the time forcing function, or also known as like the natural frequency of the structure. Since the period of the highest node for this particular project is 0.02, we just take 1/10 of that, and that's why it's 0.002. Okay. Right, then another thing we need to do is define the step number for the output. So we'll make it 5. So the analysis time step is required for producing results of time history analysis. So results produced at the interval of like the number of output steps times the number of increments. So like if 1 is specified, the analysis results are produced every 0.002 seconds. But if 5 is specified, the analysis results are produced every 0.01 seconds. So this allows you to have like a more reasonable analysis speed. Okay. So if you were to leave it at 1, you get a more detailed analysis, but it might be a little more detailed than you actually need. So that's why we're sort of increasing the time increment there. Just keep in mind that the higher the time increment is, the faster the analysis is and the less detailed it is, because it's being divided into less number of increments. Okay. So now the next thing we need to do is just click OK or Add or Apply. Oh, and actually, let me see. So let me check the damping ratio real quick. Okay, so yeah, make sure to change the damping ratio to 0.5. There we go. Okay, so now the damping ratio is there. You can click Add or Apply, and there's our first function. So now we just do the same thing for our other cases. Okay, so now for the second case, let's name it earthquake. Or actually, hold on a second, let me go back here. Okay, so sorry about that. The damping ratio here should be 0.99. So 0.05 is for the seismic loading. Okay, so I'm going to just fix that. Okay, so now that that's fixed, I can add another one. Okay, so we'll name this earthquake. Okay, then all of this essentially will stay the same. It's still linear, modal, and transient. But now, because it's my time history function, the end time will here will be 50 seconds. The time increment will still be 0.0202. And then my step number will be 5. Okay. All right, so now another important thing to remember is that data related to a sequence of consecutively loaded multiple time, that this study anyway, is related to multiple sort of time history conditions. So yeah, now, because this is the second loading, which is our seismic loading, we need to sort of use this option here, order in sequential loading. So subsequent to, just check this on. As you can see, this gets out of the gray area now. So what you need to do is you just need to select a time history analysis condition that's been previously defined that will allow you to assign something that precedes the time history analysis condition that's currently being defined. So the analysis type and the analysis method for the current time history analysis condition must be consistent with those for the preceding load conditions. So from the preceding analysis condition, you get displacement, velocity, acceleration, member forces, variables for the state of hinges, and variables for the state of the nonlinear link elements. They need to be obtained, and they're used as sort of the initial condition for the analysis. However, in the case of loadings, the loading at the final state of the preceding analysis condition is assumed to constantly remain in the current analysis condition. Only when the key final step loads constant is checked on. This option over here. So essentially all you really need to do, though, is just select a load case that will be subsequent to your earthquake. That's very simple. You only have one choice, so it's the dead load. Okay. So now the next thing we need to do is just assign our damping ratio, so it'll be 0.05. And then we'll click Apply or OK. And now we have our two time history load cases. And as you can see, the initial condition here is the dead load. So first the dead load is applied, then the earthquake load is applied, is essentially what you're doing. Okay, so now that that's done, we just need to assign our ground accelerations. So just go here. Keep in mind we've been in the load tab the whole time. So just go here to ground acceleration. And then, as you can see, we just have to select earthquake name. So first, let's go with earthquake. And then for the function direction, let's choose X, or excuse me, function direction is X, and then we'll select the first one, El Centro T. And for the second one, Y, let's select El Centro H. And then just make sure to click Add. So here we have our earthquake load. And then now we just need to create our time-varying static load. So we're doing this in order to apply the dead load to our time history now. So as you can see, we applied our earthquake load. Now we just need to apply our dead load. So once this is set, you can just click Close. It'll save. And now we just go to time history analysis data, and then go to time-varying static load over here. So this is very simple. All you have to do is select your dead load here. And then you just have to name it. So I already defined a name for it, ramp. Then click Add. Okay, so now it's listed here. And we can close it. Okay, so as you can see now, we're ready to run our analysis. So if I look here, as you can see, I have all my rigid links created. All of my forcing functions are all my time history functions. They're all listed right down here. Okay. So now the analysis itself, in order to run it, just go here and just click on Perform Analysis, and it will run it for you. So just in the interest of time, because it does take like a minute or two, I already have a completed model saved. So I'll just go here. And now I'm in the results section. So now let's check what sort of our results look like. Go to results, and then we'll go to, for example, let's say we want to take a look at our deformations. All right, so just go here to deformations, and then let's go to, let's take a look at our displacement contour. Let's go here. As you can see now, this input menu will come up that allows you to sort of filter through the results that you want to see. So under load cases and combinations, we'll go here. Let's say we want to see the maximum for the earthquake. And let's say we want to see them for all components, and let's say we want the contour on. These options here just sort of allow us to check on what sort of things we want to see. So let's also check on, let's check this on for now. Click Apply. And as you can see, it's sort of harder to see. Let me turn on the shape here. There we go, much better. So as you can see, you can sort of see where your maximum displacement is occurring and sort of how the values sort of shift from one end of the bridge to the other. Incidentally, it appears to be symmetrical. Now let's say we also want to see the deformed shape. So just go back here to the input menu, check on Deform, and click Apply. Okay, so that's an exaggerated view, but the deformation is going to look like at that particular period. And let's also say you want to get maybe some more definite values. Click on Legend here. Okay, and this option here will come up, and this will allow you to sort of gauge or get a better idea of what these contour bands represent. Another thing you can do that's really cool about MIDAS Civil is you can also use an animate option that allows you to see how the results change over the entire length of the loading period. So just click on this option here, Animate, click Apply, and then click on this function here. So it looks like a little tape deck. Click on that, and as you can see, what happens is the program will actually give you sort of this animation of how the the stresses or the deformation sort of changes over the length of the earthquake. So naturally, because I clicked on TH max, the default setting is just the maximum sort of displacement. But you can also see the other displacements that sort of lead up to that critical condition if you use this option. Okay. And another thing you can do is you can scroll through here, and let's say you want to see it, TH min or TH max for the dead load. Let's click Apply. And as you can see, displacement now is restricted to this sector area here. And if you want to see particular values just on the contour graph itself, click here, and you can see all your different values. Okay, so that's just using this function here. You can go through a lot of your different sort of results. For example, the stresses. If you want to see the beam stresses, you can go here, and let's actually turn the values off. and turn the deformation off. And you can see, sort of individually, your beam stresses. You can find your beam and moment diagrams, and it's all mainly off of these tabs here in these input menus. Okay. Now, something that's sort of unique about time history analysis are sort of the graphs that you can sort of get. So let's say, for example, you want to isolate a specific node or a specific point. Actually, let me turn the hidden view on again so we can get a clearer look at our beam diagram here. Let's say you want to, study a particular hinge just to see how it's, dissipating the energy. Let's say you want to draw a hysteresis graph. In order to do that, just go to Results, and then just go to Time History Results, or Time History Graph. And then first, you just need to define the functions that you need to use. So go here to Time History Graph. As you can see, they're already sort of defined here. But if you needed to add another one, you just go to Add a Function, and then you can define your functions from that point on. So go to Add New Function, and you just select your loading, you select your component, and you select the node that you want to see as well. So something that you might want to do. Let's say, for example, I want to see, I want to sort of study this node over here. It's connecting the pier cap to the pier. And if you want to know what number that node is, just click on this icon here, Node Number, and that allows you to sort of turn all the node numbers on. What you can do now is you can just zoom in on that node. As you can see, it's node 77. Okay, so you're just typing that node number over here to sort of focus in on that node and what's going on with the hinge, or excuse me, with the isolator. Okay, but as you can see, I've already, just in the interest of time, I've already defined my different areas, my different my different functions here. So we can just close this. So let's take a look now at how this graph is generated. So let's go to, once again, go back here to the time history graph. And what we'll do is let's turn the shear on. And then we'll, as far as the horizontal axis is, we'll select the display here. And then for the, here we can just define how far the decimal point goes. For the y-axis, let's select 1. And then let's make sure this is a time history graph, okay? So it seems as if everything's in order. Let's take a look now. And when you're ready to create your graph, just go here. Okay, and just extend it here. So here you have your hysteresis graph. So as you can see, this is just sort of shows how the dissipation occurs as the seismic loading is applied to it. So if you get, sort of like the area of like these sections here, you can get the total amount of energy that's being dissipated. All right, so that's how you create your hysteresis graph. And if you want to go back to your model, just click on this tab here, and it'll take you back to the model view. And keep in mind that this is for isolator on the node number 77. Okay, and then as far as defining that function, let me go over it one more time because I think I went over it a little bit fast last time. So here you have the function, all right, that allows you to sort of select which nodes you're studying, and also what sort of results you're looking for. So in order to add a new one, just go to Define Function, and then just go to Add. And then this will allow you to create, it'll name the function, to select the node, you can click on the screen, and then also the load case that you want to use for it, as well as the component. All right, so once you have that, here you'd have added to your list of functions. And then once you have your functions created, you just go to your graph, and then you just select from the function, which one you want to add to the vertical axis, which one you want to use for the horizontal axis. And from this point, you just need to select your decimal points and then also this type of graph that you'd like to create. Okay, so using this function, you can create sort of hysteresis graphs for each of your isolators, so you can see, how much power or how much energy is being dissipated as the earthquake progresses. Okay, so one last thing that I'd like to show you is how to create just a basic sort of time history graph. Let's say, for example, you have a particular component that you want to study. Let's say it's node number 77 again. Let's say you want to see how that displacement, what the displacement looks like as the earthquake is being loaded. So in order to do that, Once again, it's sort of the same process. Go here, put a time history graph, and then you just need to sort of define your functions. All right, so now display appear top, let's select that one, and let's close this one. Let's turn this one off. Let's add this one to the list. Okay, horizontal axis, let's make it time, so just time in seconds. And then for the decimal point, x-axis, we just want this to be 1. The y-axis should be 4. And a time history graph. Okay, so this all checks out. And we'll click graph. Okay, here we go. And as you can see, this is just a time history graph. So here's the time in seconds. Here's the displacement. And as you can see, as the sort of earthquake progresses, the displacement sort of varies, positive and negative over this length of time. As you can see, how as the earthquake sort of tapers off, so does the displacement. And you can get that for any number of nodes that you'd like, any sort of area or point. You just have to make sure to specify it in the input menu. And you can sort of save these graphs into sort of an image. They're really good for sort of larger scale reports. If you want everything displayed graphically, you can use this function with a lot of success. It'll save you a lot of time. So instead of having to sort of import sort of results from a spreadsheet into Excel, then create the graph, you can just use this input menu here, and you can create these graphs very quickly, very efficiently. Once again, you can keep these graphs over here in these tabs, and then you can always go back to your model view. Okay, so once your graph is created, you don't have to worry about accidentally deleting it. You can just go back to model view, and your tabs will be saved, or your graphs will be saved for you here in these tabs. Okay, so that about wraps it up for today's presentation. Thank you again for attending. And before I go, I just want to make sure that you guys have my contact information so that